next speaker is Ricardo Toledano. He's from Universidad Nacional del Litoral, Argentina, and he's talking about minimal value set, polynomials, and towers of Garcia, Stichtenoth and Thomas.
Thank you, Melina. Well, obviously, I want to say thanks to the organizers, including Maria and in her father's house, with a lot of power now. And yes, this guy, Stichtenoth, I think is pronounced, is kind of tricky. So, well, this is a recent work, but it's coming from years and years ago when I visited Eddie Belto in Sao Carlos. He told me, there is a connection between what you're doing and the minimal value sets. So here's something like I want to share with you. So I start with a little bit of propaganda. What is why we do start with towers? So the reason is that you want to have function fields over a final field FQ with many rational places, or cards with many rational points for applications in cryptography, coding theory, etc. And towers are like very nice objects that can give something interesting in these areas. So what do we mean by a tower of function fields? Well, it's just a sequence of function fields of FQ with some conditions, so you can work with this object. Well, first, all the fields are contained in this way, F0 in F1, F1, F2, and so on. Then each extension, we ask that they find a separable extension of degree at least 2. That means that Fy cannot be equal to Fy plus 1. FQ is algebraically closed in each Fy. That means that each element of Fy, which is algebraic of FQ, should be an element of FQ. And the last question, the property we ask that the genus of Fy goes to infinity as y goes to infinity. That means that you have a lot of, you have a chance to have a lot of rational points once you are going up in the tower. If the genus stops, you have the Hasselbalch bound that says not many points you can find. So this is what we mean by a tower, all these conditions. This is mostly the definition of tower due to Garcia and Stichtenoth. So when you have a tower, you can define these quantities, which is the genus of the tower. It's just the quotient of the genus of y divided by the degree of Ey over the bottom fields. And you take the limit, you can prove that this limit exists, is always positive, or can be infinite also. And then if you take the number of rational places of y, you do something similar, consider this quotient, you can prove that this limit exists, and it could be 0, but never could be infinite, and it's called the splitting rate of the tower. With these two quantities, you define when a tower is good or asymptotically good. You have to have a positive splitting rate and find a genus. Otherwise, if this is 0 or this is infinity, the tower is called bad. This is an equivalent definition, which is taking these quotients, the degree of the fields goes away, and you take the number of rational points divided by the genus of each field. To take the limit, you can prove the limit exists, and if good, the limit is positive. Otherwise, the limit is 0, means that the tower is bad. So this is the limit of the tower, and that's the main interest in towers. You want to have a lot of good towers over any final field. That will give you examples of function field with many rational points and applications to coding theory, cryptography, etc. So related to this quantity of the limit is the so-called Ihara constants. Now how you take the genus, go to infinity, and you consider all the function fields, the fixed genus G, and all the rational places, and look for the maximum number of rational places when you fix the genus. You can prove that this limit exists and is called the Ihara constant. So one problem that it was solved many years ago, was, is this constant always positive? Well, that was answered by Serre, but previous to that was there were upper bounds. Is the Dirichlet-Blandung upper bound is a square root of q minus 1. And when the q is a perfect square, it's exactly equal to the square root of q minus 1. But when the q is not square, nothing is known except the lower bounds. Serre, using class field towers, proved that this quantity is not trivial. It's always positive, but use class field towers, right? You have you take the Hilbert class field of this field and go up, you get a tower, and you can bound the constant at the q for this other constant. So this is the non-triviality of the inherent constants. But if you take a tower, you always have this inequality. So if you had good towers with positive limit, you get good lower one for the inherent constant. So this is another reason to study towers, to build new lower ones for the inherent constant. So when you reach the limit of the tower is exactly the inherent constant, you say that the tower is optimal. So far, the optimal towers are known over final field with a square cardinality. And these examples of optimal towers were used to construct like a really nice codes over a final field FQ, linear codes, which is they're called algebraic geometry codes, and beating the so-called Gilbert-Bashamov bound. So that was like a big step in coding theory. And you can see all these things I'm talking about in the classical Stichtenoth book, Algebraic Function Fields and Codes. There are many other books also, but this is like the classical one. So the concept of recursive towers is a special kind of tower that was defined by Garcia Stichtenoth in the 90s. So here you have a tower of function field. It's called recursive if you have a sequence of transcendental elements of FQ, a polynomial in two variables, so that you take x1 and xy plus 1 is the root of this polynomial. And the fields are defined sequentially in this way. So this is the rational function field. Then you add the next root x1. Then you add the next root x2, and so on. And then you get a tower. And you ask for the degree is always the degree in the y variable of this polynomial. So this is the concept the Garcia and Stichtenoth study. And this is recursive because you use the same equation in every step of the tower. That should give you like more chances to find like for instance, the dimension of the Riemann-Fock spaces, because you have everything more or less controlled with by this polynomial. So that was the hope in defining these recursive towers. A special kind of tower was studied by Garcia, Stichtenoth and Thomas in 1997. And the equation is given by this shape. It's y to the n, x to the d, hx, with these conditions. Always n has to be bigger than 1, otherwise you will have a linear equation here and you don't get a tower. Q has to be congruent to 1 mod n. This gives you that all the nth root of unity are in FQ. N and d have to be coprime, and the polynomial h have a non-constant 0 term. And the main coefficient of h of x has to be an nth power in FQ. So with these conditions, they define this with this equation, then define towers, and they can prove. Well, we call this tower like a GS type, and the polynomial in the right-hand side we call the GST polynomial with all these conditions that they are here. So these guys prove that with that equation you always have positive splitting rates. So that's one of the conditions to have a good tower, positive splitting rates. And the other problem was the genus. You have to have finite genus of the tower. And for that, they ask another condition, which is the main topic of this talk. You need to have some set, finite set in the algebraic closure of Q, such that the 0 is in S, and every time you take an element in S and look for the roots of this polynomial, all the roots are again in S. So this is a very strong conditions on the polynomial. Few examples were found, but suffices to say that many examples of this kind of tower are still unknown. But they proved like a couple of examples that giving like an example of a good tower on almost every final field. That is the interesting point of this family. So, but you have to take the final field with the cardinality, which is not a prime field. So have to be like a P to the S with S bigger than 2. So, and in this way, they give like an alternative proof of the non-triviality of the Harran constant, but for a final field of this with the cardinality. So what about prime fields? Well, several years later, Lenstra proved that you cannot find a tower of the GS type with would be asymptotic behavior over prime fields. That means that the problem was that if you take a polynomial satisfying all the conditions of the Garcia, Stichtenoth, and Thomas ask, you will never find over a prime field congruent to 1 mod n, you will never find a final set in the auxiliary closure of P, such that the 0 is in S and the other root of this polynomial for each element in S are again in S. So that was like a bad news, but still, despite this problem with the prime fields, the family of towers of the GS type are like give examples of good towers over every non-prime final field. And you ask, well, if you have like for almost any final field a good tower, how about the application of this tower to coding theory? Well, one of the main applications of these towers in coding theory are the asymptotically good family of coding linear codes over a final field. But for that, in order to use a tower to produce a asymptotically good family of codes, you need that the limit of the tower has to be greater than 1. So that's we want to show now that in the family of this tower defined by Garcia, Stichtenoth, and Thomas, there is only one example of limited bigger than 1. We deduce that the situation with the help of the minimal value set polynomials. So I want to, Luciani was talking about minimal value set polynomials, so I want to just review briefly. So you take the value set is as the images of the polynomial when R is in FQ. Always you have the value set is at least this quantity, and when this quantity is reached, it's called a minimal value set polynomial. If you can generalize a little bit this definition by considering a non-empty set of FQ. So you have the same definition. We call it S value set, but now the values of F are reduced to S, to the set S. So when S is FQ, we don't write the FQ here. And you have the same situation. You can prove that the S value set is always bigger than the cardinality of S divided by the degree of F for any finite subset of FQ. So when you reach equality, you call S minimal value set polynomial. So it's a small generalization of the value set definitions. The thing is that the condition of ask for Garcia, Stichtenoth, and Thomas can be described in this way, in a more general situation like this. So you take a polynomial of Q and you say a positive degree, and you say that this is an S-phi polynomial if there exists a polynomial over FQ and a finite subset of the algebraic closure FQ, such that for any beta in S, the root of f of alpha equal to f phi of beta are again in S. That's exactly the definition, the property asked by Garcia, Stichtenoth, and Thomas in the case that phi is x to the n. So this is like a slight generalization of the condition asked by Garcia, Stichtenoth, and Thomas. So in this language, what you're asking in order to have finite genius in a tower is like you have this polynomial, you want it to be an S x to the n polynomial in the sense of these definitions, right? So this is like the result linking the behavior of minimal value set polynomials with the condition asked for Garcia, Stichtenoth, and Thomas. So suppose you have an x to the n polynomials of degree n at least 2 over fq for some set in fq. Say like these guys lambda 1, lambda k are non-zero elements. And suppose that we take the root of nth root of unity, we call them mu sub n. If q is congruent to 1 mod n, then you have that this set is a subset of q. And this is the first result linking these guys. If you have an s x to the n polynomial, f has to be an s minimal value set polynomial. So this guy f satisfies this equality for that set S. Then you can give double bound for the size of S. Even more, the value set of F and S value set of F is exactly the S value set of x to the n. Also, the size of S has to be at least n plus 1. And this means that this k has to be bigger than n. And you get equality exactly n plus 1, and these guys, this quotient are the root of unity when the value set of x to the n is exactly 2 for a divisor of q minus 1 that is not q minus 1. In this case, you can prove easily that the s value set of f is just these two guys here. And if one of these quotient is not nth root of unity, you prove that the size of S is at least 2n plus 1. This gives you the idea of the size that the set have to in order to have the condition of Garcia, Stichtenoth, and Thomas. When S is exactly q minus 1, you can prove that S has to be fq, the whole fq, and in particular, f is a minimal value set polynomial in the usual sense. The value set is just 0, 1. Because it's coincide with the x to the n, and x to the n reduced to the fq is 0, 1. And f has to be of this shape. This is a result of Carlitz. You can see this result in the classical paper of Carlitz on minimal value set polynomials. So you have this the connection between a property giving you a asymptotically good tower with the minimal value set polynomial. And we can use this to study the situation of how good are these towers of Garcia, Stichtenoth, and Thomas to have a good code. So they prove that this tower have this limit, this lower bound from the limit, and this bound cannot be improved because in the case of q equal to 4, it's reached this bound, this lower bound. And so if you want to have a limiter bigger than 1, so the tower is good for studying asymptotic problems in coding theory, you need to have the set S cardinality less than 4. But for our results, the set S has to be at least n plus 1 element. So that means that n has to be equal to 2. In n equal to 1, you don't get a tower. So the only possibility is that n has to be 2. So if you want to have a tower of Garcia, Stichtenoth, and Thomas good for application in asymptotic problem in coding theory, it has to be a quadratic polynomial, right? And q must be odd and bigger than 9 because our Lenstra result said over prime field, it doesn't work. So you have to go to at least F9 and the cardinality has to be bigger than n, bigger than 9 or more. So what we can prove is that with the quadratic equation, like doing a lot of manipulations, we can prove this result. The only tower of Garcia, Stichtenoth, and Thomas satisfying this condition is this one here, is y2 squared 2x times x minus 1. And it has to be over F9. So in what sense is that the only one? Any other tower, quadratic tower of this shape, being asymptotically good, it will be exactly like this equation after a change of variable. So all the towers you get there are infinitely many, but they have to be equivalent to this one here. So there is actually one and is over F9. So this is like a kind of surprising result because it's a huge family of towers over almost any finite field, but there is only one example that could be good for studying asymptotic problem in calling theory. So this problem was as I said at the beginning, was because of an observation by Erivelto. And with Erivelto, we were studying like the reciprocal situation, and we couldn't reach any interesting results. So like it's like an open problem now. It's going in the opposite direction. So if you have a polynomial with all the conditions asked by Garcia, Stichtenoth, and Thomas, and is a minimal value set polynomial, when is this guy is an Sn x to the n polynomial. So when this has this property of absorbing all the roots in the set of Garcia, Stichtenoth, and Thomas. So that was like a, I don't know, we couldn't answer any interesting question. So it was left like this, and still I don't know what to say in the opposite direction. This opposite direction is very interesting, but it will give you a lot of more examples of asymptotically good towers. They are maybe not good for studying asymptotic problem in coding theory, but they can be good for studying other problems in cryptography or coding theory. So, well, that's the one all I wanted to say.